Hi and welcome back to another lesson in the physics video series. Today we're going to discuss horizontal projectiles and explain how this form of projectile motion from the turning point at the high point of the y max is the right half of the symmetrical parabola. Alright, let's get started. If you recall the full parabolic motion of a projectile, you'll remember that there is a rising zone and a falling zone. If you start your projectile at the top, say from a tall building, and you throw a rock straight off, you're really only dealing with the free-falling zone of the projectile, which is essentially a free fall problem and constant velocity problem. We're going to take a look at these right now. If you throw a rock from a high building horizontally to the side, it will fall while moving at a constant speed to the right. It will follow the second half of the parabola, which is the free fall zone. Let's say I threw a rock from a height of 100 meters at a speed of 50 meters per second. This rock will follow the parabola from the turning point on the axis of symmetry all the way to the ground. This is the free fall zone of the full parabola. Alright, let's say I throw a rock at 50 meters per second from a height of 100 meters. And I'm going to throw this rock horizontally. I could throw it at an angle, but that's a much more complicated problem, and we want to stay simple for now. If I throw the rock to the right at horizontal speed of 50 meters per second, that is the Vox. Since it's going to free fall, its initial vertical speed will be 0. As this rock follows the parabola, the blue vector, which represents the vertical velocity in the negative direction, is increasing, and therefore the arrow of the vector gets longer until it hits the ground. The Vox will remain the same the whole time because there is no sideways gravity. So let's take a look at the same steps we used for the full parabola and apply that to the half parabola problem. As I mentioned before, the first step is usually to find the components. So the initial velocity happens to be exclusively along Vox. The angle theta is actually 0. So VO cosine theta, cosine 0 is 1. So the horizontal velocity component is the entire velocity, which happens to be 50 meters per second. The vertical velocity is the velocity of free fall, and its initial velocity in the vertical direction is 0. Let's take a look at the picture, and you'll see the red ball being thrown to the side. There is a green vector arrow, but there is no blue vector arrow. That means that the vertical speed that you see in these two positions is absent in this initial position. The second step is always to find the time of flight, and in this case the time of flight is simply the free fall time, otherwise known as t down. We're going to use equation 4 and solve for t. We know that d equals VOT plus 1/2 AT squared, and the d is on the y-axis, and the VO is the VOY, which is 0. And since you're heading down in the negative direction, the negative from the gravity drops out, and you get y equals 1/2 GT squared. Solving that for t, you get the square root of 2y over g. This is a universal statement which really should be memorized. Inputting the values that we have, the square root of 2 times 100 over 9.8, it takes 4.52 seconds to hit the ground. So whether I threw the rock to the side from a height of 100 meters or just dropped it from the height of 100 meters, it's only going to take 4.52 seconds. The time to fall and the time to go to the side and hit this range point is the same. This is a common trick that students miss when doing these problems. The time it takes to fall and move to the side is the same. In this case, it was 4.52 seconds. Step 3 is the same. We're going to find the range, and this is using equation 1 and the answers from steps 1 and 2. So we know that R equals Vox t, and that comes from D equals VT. R stands for the range. You could use the letter D. And V is the V on the x-axis, which happens to be the Vox. Steps 1 times step 2. So 50 meters per second times 4.52 seconds, which was calculated in step 2, gives you a range of 225.8 meters. As we said before, this ball would have taken 4.52 seconds to fall straight to the ground. But it is falling straight to the ground while moving sideways, and that's why it lands over 200 meters away off to the side on the x-axis. Step 4 usually asks you to find the y max. In this particular case, the y max, or the height, was given as 100 meters. But what if you didn't know it was 100 meters and you did know the free fall time, or the time of flight? So you would then take equation 4 and you would solve it for d. VOT plus 1/2 AT squared. This formula converts into y equals VOY t plus 1/2 GT squared, and the VOY is 0. So the height, d, which now turns into the letter y for the y-axis, is equal to 1/2 gt down squared. We know that the t down was solved in step 2, and we input that number right here, multiplied by half of gravity, and of course we have the full free fall height, which would have returned a value of 100 meters. Something should be noted that's very important about step 4. Either you are given the maximum height and you have to find the free fall time, or they give you the free fall time and they want to know from how high did the projectile descend. So you have to be given one piece of information or the other. Either you're given the height and you find the time down, or you're given the time down and you have to find the height. And finally, step 5, the final impact velocity. Notice I didn't say impact speed. Because it's a velocity, you need to know the value of the speed, which is the VF, but you also need to know the angle theta, which is the direction. The speed plus the angle make the velocity. In order to do this, you must find the VFY, the vertical freefall impact speed, and then Pythagorize that with the original Vox. The Vox was given, but the VFY, the blue, must be determined. Then use Pythagorean theorem to find this hypotenuse, which is the V final. So that's the impact speed. Like the javelin in the last video, when the javelin sticks into the turf, you want to know the speed at which it impacts and the angle that it makes to the turf. So how do we do that? Well, we should recall that Vox was given and it is a constant, but the VFY can be found in 2 different ways, and that's up to you. It depends on what information you have, or could use both to double check. You can recall that formula 3, VFY equals GT down, solve for VF, and you can determine the vertical impact speed. Or you could have used the height, and you could have done the square root of 2gy, which is formula 5, solve for VF. So formulas 3 and formula 5 both give you the vertical impact speed component. One of them depends on time, that's equation 3, and the other one depends on height, that's equation 5. In this case, I chose to use equation 3, and I knew that gravity, 9.8 meters per second squared, will be multiplied by that free fall time, t down, of 4.5 seconds. And then I got VFY equal 44.3 meters per second. And I make a note here. This blue vertical vector is not the answer, but the vertical component of the impact velocity. You now have to use this number, 44.3, and Pythagorize it against the original speed, which was 50 meters per second. The Pythagorean theorem would look like this. V final equals the square root of Vox squared plus VFY squared. This is the x component, this is the y component. Vox squared, 50 meters per second squared. So the green was given, and this blue, 44.3, was just determined using equation 3. You could have also used equation 5. So when I combine these, I Pythagorize, I get a magnitude of 66.7 meters per second. So this red vector is the real answer that we're looking for. That is the impact velocity. We know the speed component of it now. That's the Pythagorean. Gives you 66.7. And what is the angle? The angle equals arctan of y over x. The y component divided by the x component. Since this y component is pointing down, it has a negative. VFY divided by Vox, negative 44.3 over 50 gives you a negative angle of 41.5 degrees. So this is 41.5 degrees below the horizontal, and it impacts at the velocity of 66 meters per second. All in all, the horizontal projectile problem is not too difficult, especially if you remember that it's simply a free fall problem and a sideways constant velocity problem happening at the same time. As always, you find the components, then the time of flight, then the range, then either the height or the time down, and then finally, the most difficult part is the impact velocity, which I explained here. And this step is exactly the same as the full parabolic projectile problem. This explains everything you need to know about a horizontal projectile problem, and while the Regents may never give you every single one of these steps, they will ask you a few of them. So as long as you know the whole cycle of the solution, you can start at any step and work your way back. We say back solve to what's missing and what's needed to be found. I hope you enjoyed this video. Thank you for watching, and we'll see you in the next video.